Madeline Dawsey here with us today. She's recently started a position at the University of Texas at Tyler. And yeah, she's going to tell us about a really cool connection between modular forms and Ramsey theory.
All right, thank you. And thank both of you, Ian and Larry, for setting this whole thing up and inviting speakers to speak virtually. It's been really great. I've really enjoyed hearing all of the talks. Yeah, so I'm excited to talk about some Ramsey theory today. So this is something in graph theory. And I never did any graph theory before this, but I think it's really cool that there is a connection with modular forms. And this is joint work with Dermot McCarthy, who's at Texas Tech. So I want to start just by talking about how these connections work in kind of a basic sense, and then I'll spend most of the talk kind of going through theorems about connections and giving examples of connections and then proving them. So here's just an overview of how everything's related. Ramsey theory here on the left, that's a part of graph theory. So I'll talk about what Ramsey theory is, but it turns out these functions called hypergeometric functions are really good at detecting certain properties of the graphs that we look at in Ramsey theory. And so there's a connection here between hypergeometric functions and Ramsey theory. And there's also lots of examples of finite field hypergeometric functions being connected to elliptic curves as well, because it turns out they're also really good at counting rational points on elliptic curves. And so this lower connection is here. Can you guys see my mouse that I'm, yeah, okay.
Yeah.
So this lower connection, there's lots of examples of that. And then if you know the modularity theorem, there's automatically a connection between elliptic curves and weight 2 new forms. So there's like infinitely many connections here on this vertical strip. And so kind of in a roundabout way, that means modular forms are related back to hypergeometric function evaluations, which are related to the graph theory. But it turns out there's more interesting of a connection. So that's kind of the most basic connection with the weight 2 new forms. There's actually connections between higher weight new forms and hypergeometric function evaluations. And so that's kind of more interesting to me because those are ones that don't come from the modularity theorem. And there are several examples of higher weight new forms having these formulas relating them to hypergeometric functions and then back to the Ramsey theory, which was surprising for me. And so what I'm kind of looking into right now, it's not part of this talk, but it's kind of further work that I'm looking at, is possibly higher dimensional things down here, like K3 surfaces seem to be related to weight 3 new forms. And then if you go even higher than that, if you look at like Calabi-Yau threefold, so those are dimension 3, then those seem to be related to weight 4 new forms. And so I really wonder how deep the connection goes with these higher weight modular forms and the higher dimensional manifolds here, and how those are all connected back to the hypergeometric functions in the center. So that's kind of a brief overview of why I care about this problem that we worked on. And so now let's get into kind of what all the pieces mean. I'm going to start with Ramsey theory. This was kind of the motivation, is that Ramsey theory ties into all of those things. So what is Ramsey theory? Well, it's about graphs. So if you start with a graph G that is complete. So what that means is you have some vertices, so they just look like points, and we usually arrange them in kind of a circle. And then you have some edges between the vertices. But complete means that every pair of vertices has an edge between them. So like all the lines are there that could possibly be there. So you have a complete graph with colored edges. So you have like some number of colors. You can just decide how many colors you want. And each edge you color one single color. So we're going to let R be a positive integer. Now the fundamental question in Ramsey theory is, how large must a complete graph G be in order for it to be guaranteed that it has a complete monochromatic subgraph of order R? So order R means R vertices. And so I guess when I first saw something like this, I didn't know that that would even be true. Like, how can you know that if you have a large enough graph, you have to have a complete subgraph all of the same color? But that is true. This is always going to work if you let your graph be large enough. So these complete graphs get really, really complicated when you have more and more vertices. And so it's basically saying that there's some kind of structure in smaller pieces of this big chaos of the large graphs. So here's the theorem, Ramsey's theorem. It says that this always exists. So let C and n1 through nc be integers. There is a number r depending on those integers, such that if the edges of a complete graph of order r are colored with C different colors, then it must contain a complete subgraph of order ni, whose edges are all the same color I. Okay, so it has to work. It always has to work if you let your graph have enough vertices. So when we say Ramsey number, we're usually talking about two colors. So Ramsey's theorem works for any number of colors you want, but usually we're talking about just two colors when we say the Ramsey number, and we usually make them red and blue just because those are like the standard two colors that people choose. So R of Mn is the smallest number of vertices that a complete graph has to have, so that when you color the edges all either red or blue, you have either a complete red subgraph of order M or a complete blue subgraph of order N. So some examples are known of this, like some people have computed some Ramsey numbers. Not a lot of them, but some of them have been computed. So first, R of 3, 3. That was a big one. So that's saying we want to know the smallest number of vertices that a complete graph needs to have, so that it either has a complete subgraph of order 3 that's red or a complete subgraph of order 3 that's blue. And so what's a complete subgraph of order 3? Well, it has 3 vertices that are all connected by edges, so that's a triangle, right? So we're looking for either a red triangle or a blue triangle. Was there a question in the chat?
No, carry on, just a mild comment.
All right, sounds good. So we're looking for a red triangle or a blue triangle. And so it's been proven that R of 3, 3 equals 6, meaning if you start with 6 vertices and you color all the edges either red or blue, you have to either have a red triangle or a blue triangle. And this graph here is the example of a graph with 5 vertices that does not have a red triangle or a blue triangle. So it's like the counter example that shows that R of 3, 3 has to be at least 6. So you might have heard this another way. This is called the friends and strangers theorem, if you've ever heard of that. In any party of 6 people, either at least 3 of them are pairwise mutual strangers, or at least 3 of them are pairwise mutual acquaintances. So this is saying the same thing. If you have 6 people at a party, those are like the 6 vertices, then you have to either have a red triangle, like 3 people who all don't know each other, or a blue triangle, so 3 people who all know each other. Okay. All right, so let's look at another example. R of 4, 4, that's looking for the smallest number of vertices you need, so that you have either a complete subgraph of order 4 that's red or a complete subgraph of order 4 that's blue. So complete subgraphs of order 4, those are 4 vertices, and so you have all the edges between them. So you have a square, and you also have the diagonal pieces. And so it's been proven that R of 4, 4 equals 18. If you have any less than 18 vertices, then it's possible to find a graph that doesn't have a complete subgraph of order 4 that's red or a complete subgraph of order 4 that's blue. And so this graph to the left, this is called a Paley graph of order 17. So I'll get into what that is. But this is actually the counterexample for R of 4, 4, saying that it has to be greater than 17, because this graph has 17 vertices. You'll notice it's not a complete graph. And it's also not colored, but we're going to learn in a minute that it means the same thing. So this is still a counterexample because this graph doesn't have a complete subgraph of order 4 in it. Okay, there's some other known values for the Ramsey numbers into 2 colors. So R of 2, n is known, and that's pretty easy whenever one of the numbers is 2, because then you're just looking for when you have an edge of a certain color. R of 3, 4 through R of 3, 9 are known. R of 4, 5 is known. And other than that, all we know, especially for these diagonal Ramsey numbers that we care the most about, the R of 5, 5 up to R of 19, 19, those are known as ranges. So we don't actually know the values of those Ramsey numbers. We only know that they live in some range. And so the lower bounds usually come from something like what I've talked about already. You find a graph with a certain number of vertices that doesn't have a complete subgraph of some order. And that's going to be a lower bound. And then there's like elementary upper bounds you can use to get the top part. And so for these larger cases, they don't sandwich your number. very well. And so these ranges get really large. And so the point is, this is kind of a hard problem. Whenever you get more and more vertices, these graphs just become so complicated and hard to study. And it's really difficult to even get a computer to like spit them out. If you wanted to make a complete graph with 43 vertices, and then look at all possible red-blue colorings of that graph, like that's a lot of computing power that you would need. So these are difficult.
Doesn't Erdish have a funny saying about this? Like if aliens were gonna invade the Earth, didn't he say? I guess it's what if the aliens invaded Earth and they said you have a year to find the value R55, I think. We devoted all the resources of humanity to that for 1 year, we could probably do it. But I guess if they ask for presumably R of 66, then we should probably prepare for war rather than actually trying to do it, because there's no hope of doing it in a year.
Yeah, I think I have heard that. Yeah. Great. Yeah, so these are difficult. So one of these ones we talked about, R of 4 equals 18. I'm going to talk a little bit more about that because the Paley graph comes up, and that's going to be a big thing in this talk. So in 1955, Greenwood and Gleason proved that R of 4 equals 18. And here's kind of some bullet points about how they did it. First of all, I mentioned that the graph we saw on the previous slide, it's not colored red and blue, and it's also not complete. So how can you use that to tell us anything about R of 4? Well, it turns out Ramsey numbers into two colors can be restated in terms of graphs and their complements. So if you think of the blue edges as being like the edges that are there, and the red edges as being edges that are not there, then the red edges are like the complement of the blue edge graph. And so if you just restate Ramsey numbers like that, you don't have to start with a complete graph. You're just looking for the smallest number of vertices required so that you have either a complete subgraph of order 4 in the graph, or a complete subgraph of order 4 in not the graph, in the complement of the graph. Okay, so the graph itself is like blue and the complement is like red. Well, that Paley graph on the previous slide, it's self-complementary. That means it's isomorphic to its own complement. And so if you can just show that that Paley graph doesn't have a complete subgraph of order 4, well, then automatically its complement also doesn't have a complete subgraph of order 4 because those are the same graph. So that gives you this lower bound. It says that R of 4 is at least 18. And then you can use elementary upper bounds to show R of 4 is less than or equal to 18. So it has to be equal to 18. Okay, so these Paley graphs are pretty natural to look at when you're trying to study Ramsey numbers into two colors because they're self-complementary. So you only have to look at the graph and see whether it has a complete subgraph of some order, and then automatically you know whether its complement does as well.
So quick question, did you define the Paley graph? Oh, I see, it's on the
Next slide.
Okay. All right.
Yeah. No, you're good. Okay, so now let's define what the Paley graph is. For Q, a prime power congruent to 1 mod 4, the Paley graph G of Q is the graph with vertices from FQ, so like 0 through Q minus 1. And A and B have an edge between them. That means AB is an edge. If and only if A minus B is a quadratic residue, mod Q. So this is the Legendre symbol here. So again, Paley graphs are pretty natural to look at with Ramsey numbers because they're self-complementary. So if you want to prove this, I just have a short proof here. If you take any vertex in your Paley graph, so any element of the finite field, the way that you show they're self-complementary is you come up with a map between the graph and its complement and show it's an isomorphism. And so here's a map. If you send x to x times k mod q, where k is a non-residue, then what does that do? Well, it's going to send residues to non-residues, and it's going to send non-residues to residues. So everything that's in your graph is going to end up not being in the graph you get when you use this map. And all the stuff that wasn't in the original graph will end up being in the graph that you get when you use this map. So you'll get the complement, and those are isomorphic. So another thing about Paley graphs is they're undirected, and this is important because it keeps it's a difficult problem. Ramsey theory is difficult, but at least the graphs are undirected. You don't have to worry about like the edges only going in one direction and having arrows. And so the reason that Paley graphs are undirected is because if A minus B is a quadratic residue mod Q, well then B minus A is also a quadratic residue mod Q because Q is 1 mod 4. And so if -1 is a quadratic residue mod Q, then A minus B and B minus A are the same thing. And so this is kind of a basic proof that you might learn in like an intro to number theory course. But if you take a generator of FQ star, it has order Q minus 1. So G to the Q minus 1 is 0 mod Q. Well, that's a difference of squares, so you can split it up. And so either G to the Q minus 1 over 2 is 1 mod Q or -1 mod Q. Well, it can't be 1 because the order of G is Q minus 1. So it has to be -1. And we also have that Q minus 1 is divisible by 4. So you can split that up into G to the Q minus 1 over 4 squared. And that shows that -1 is a square mod Q. Okay, so they're undirected. Great, so what Greenwood and Gleason were able to show is that G of 17 has no complete subgraph of order 4. That's all they looked at. And so this kind of raised the question, well, how many complete subgraphs of order 4 does a general Paley graph have? Like not just G of 17, but the other ones as well. And so this is what Evans, Pulham, and Sheehan studied in the 80s, the early 80s. And they were able to prove that if P is 1 mod 4, so they didn't do this for prime powers, but it's pretty easily extended to prime powers. But if P is 1 mod 4, and P is x squared plus y squared and y even, so you can write it like that uniquely since P is 1 mod 4, then the number of complete subgraphs of order 4 contained in G of P. So we use this K4 to mean the number of complete subgraphs of order 4 in the graph. And so they found this formula for it. Great. So there's a thing called a generalized Paley graph that you might want to look at next. And so the way that these generalize the Paley graphs is that instead of looking at quadratic residues, we look at kth power residues. So here's the definition of a generalized Paley graph. We're going to let k be an integer at least 2, and let q be a prime power such that q is 1 mod k if q is even, or 1 mod 2k if q is odd. Then the generalized Paley graph, it has a subscript k on it, is the graph still with vertex set fq, but now you have an edge, AB, if and only if A minus B is a kth power residue. Okay, so these guys are not self-complementary anymore unless you have k equals 2. And the k equals 2 is the original Paley graph. And so that basically comes from the fact that like you have the same number of quadratic residues as quadratic non-residues. But then when you look at higher powers, you're not going to have the same number of kth powers as non-kth powers. And so these are not going to be self-complementary, but they're still undirected. So that's what this congruence condition here tells you. That's like doing the same thing as the Q congruent to 1 mod 4 before. That's saying that -1 is a kth power, mod Q. Okay, so these generalized Paley graphs, you might want to look at the number of complete subgraphs of order 4 in those now that Evans, Pulham, and Sheehan looked at the original Paley graphs. And so that was our first goal, was to just find a formula for the number of complete subgraphs of order 4 in these generalized Paley graphs. And then while we were at it, we still had to look at complete subgraphs of smaller orders. And so we might as well find the number of complete subgraphs of order 3, the number of triangles in GK of Q. And then we wanted to use those to get lower bounds for these multicolor diagonal Ramsey numbers. So RK of 4 is like R of 44444 K times, and RK of 3, because whenever you can show that the number of complete subgraphs of order 4 is 0, then that'll be a lower bound, right, for your Ramsey number. And so we were hoping we would get better bounds than what's already known. And then we also, this was kind of the most interesting part to me, was identifying connections with modular forms and elliptic curves to this graph theory. Okay, so I'm going to go ahead and show the main results, and then I will spend several minutes defining everything that's in these theorems. So here's our first main result. If chi k is a character of order k, then the number of complete subgraphs of order 4 in the generalized Paley graph can be written like this. So this big nasty expression with these 3f2 finite field hypergeometric functions that I will define. And notice that it's a sum over, it's like 5 sums. It's a sum over 5 different things in ZK. And then we were able to, as a corollary, find lower bounds for the Ramsey numbers, right? So if you find the largest Q such that this formula gives 0 on the right side, then that's a lower bound for these Ramsey numbers. And so we found that 18 is less than or equal to R of 4, 4. Well, that's already known because we knew that R of 4, 4 equals 18. We showed that R3 of 4, R of 4, 4, 4 is greater than or equal to 128. And then R4 of 4 is greater than or equal to 458. So we were really excited about the first two because those match the best known lower bounds for these numbers. But then the third one, unfortunately, does not match the best known lower bounds. And so what happened there is that the Paley graphs, the generalized Paley graphs, when k equals 4, that's no longer the right graph to look at to get the best lower bound. And the main reason is just because you're not self-complementary anymore. So a better idea would be to look at like a higher dimensional analog of self-complementary for the larger k. And maybe that would get you closer to the best known lower bound. But the Paley graph is not the right thing to look at anymore once you get to k equals 4. Okay, then our second main result is that we have a formula for the number of triangles in GK of Q. And it's in terms of this J function here. This is a Jacobi sum. So it's a character sum. I'll define it in a minute. And so again, we got a corollary that gave lower bounds for these Ramsey numbers. And again, the first two matched the best known lower bounds and the third one did not. Okay, so again, the generalized Paley graphs are not the right thing to look at anymore when you're trying to bound these Ramsey numbers. Okay, so I'm going to talk a little bit about hypergeometric functions and what they are and what we know about them and their connections to elliptic curves and modular forms. So I'm going to let FQ star hat be the group of multiplicative characters of FQ star. And then for two characters A and B, this is how the Jacobi sum is defined. J of AB, it's a sum over all elements of the finite field. A of A, B of 1 minus A. We're also going to define this symbol AB just to simplify notation. And so the definition of the hypergeometric functions will fit on one line. And so here's the definition of a finite field hypergeometric function. We have characters A0 through AN and B1 through BN. And then we have some element lambda in the finite field. So n plus 1 Fn is defined in this way. You have Q over Q minus 1 times a sum over all the characters of all of these symbols that all have these Jacobi sums in them. And then times chi of lambda. So lambda is like what you're evaluating the finite field hypergeometric function at. Okay. So these are difficult to evaluate. They're not easy to evaluate. There are some of them that have been evaluated at specific values of lambda. And they're usually for lower n, for really small n. So for example, if P is an odd prime, then we know that 2F1 of, so this phi P, this is the character of order 2, mod P, and then this epsilon P is the trivial character. And then if you evaluate that at 1, then you get this, phi P of minus 1 over P, and it's the negative. Okay, so we know that one value. We also know this other value for 3F2. We know if you take those same two characters, the one of order 2 and then the trivial one, and you plug in lambda equals 1, then depending on whether P is 1 or 3 mod 4, you either get 0 or this 4x squared minus 2P over P squared. Okay, so sometimes it works out really nicely. We also have a lot of really great formulas from Green, who made a lot of progress on hypergeometric functions. And he proved, for example, this one formula for n plus 1 Fn in terms of a sum of nf n minus 1. And so this is really useful because it basically gives the hypergeometric functions as traces of the lower hypergeometric functions. So this is really, really nice to simplify things sometimes. And we'll see more theorems of Green later. But also we have connections to elliptic curves. So let's see a couple of examples. And you can find these in the web of modularity that Ken Ono wrote, for example, among other places. So if we let lambda be a rational number that's not 0 or 1, and we look at this elliptic curve in this Legendre normal form, and it has some L function. So I'm not going to get into what this is, but it has some L function attached to it that has these coefficients that I'm calling 2a1 of n lambda. Well, if P is a prime of good reduction, which means here that it doesn't divide the conductor of the elliptic curve, then we can write these coefficients of this L function at the prime P in terms of a 2f1 finite field hypergeometric function evaluation. So it's evaluated at the lambda. And so we also have a formula for counting the number of points on the reduction of this elliptic curve mod P. So the formula for the number of points is P plus 1 minus that coefficient. And so when I said earlier, finite field hypergeometric functions are good at counting points on elliptic curves, this is why, because we have this formula for the number of points, and it has to do with the coefficients of the L function that in certain cases can be related back to finite field hypergeometric function evaluations. Okay, so 2f1 is good at counting points on this curve. And then if we want to look at another example, here's a slightly more complicated elliptic curve. It also has an attached L function with these coefficients that I'm calling 3a2 now. And so now we have a formula relating the square of those coefficients to a 3f2 hypergeometric function. And so sometimes I've heard Ken say 3f2 is like the square of 2f1, like in quotes. And so this is kind of saying that. So you get like a 2f1 squared, that gives you a 3f2. Okay, so it makes sense that this is squared here. And then we still have this formula for the number of points on that elliptic curve, mod P, in terms of the coefficients of that L function. Okay, so most of the connections with elliptic curves are going to be with 2f1s, but if you like square things, you can get connections with 3f2s. Okay. And so then if you kind of factor this through the modularity theorem, then you'll get something like this. If you have a rational number lambda that's not 0 or 1, and n lambda is the conductor of that first elliptic curve we saw 2 slides ago, then there is a new form of weight 2 and level the conductor that has this formula. So what the modularity theorem says is that the P Fourier coefficients match the coefficients of the L function of the elliptic curve. And so we have this formula for the coefficients. And then you can do this as well for the other one. So for the other elliptic curve, we'll have the square of the coefficients, and that's related to this 3f2. Okay, so there are lots of relationships like this because anytime you get a connection to an elliptic curve, you're automatically going to have a connection to a weight 2 new form. But the really interesting thing is that there are more connections to modular forms than just the weight 2 ones coming from the modularity theorem. So if you let F be the unique new form with CM in this space, so it's weight 3, it has coefficients alpha of n. Okay, well then we know a formula for alpha of P. This is already known. We get 2p minus 4y squared. And so that actually looks like something in the formula that Evans, Pulham, and Sheehan found for the number of complete subgraphs of order 4 in the Paley graph. So in special cases like this, you can even relate it all the way back to the graph theory side, because something in this formula looked just like the P Fourier coefficient of this weight 3 new form. So that's kind of cool. And there's more connections that we have conjectured. So I'm only going to show like 2 of them here, but we're working on 13 more. And you can kind of search for these in smart ways based on like the Hecke algebra and like other things that you know about these modular forms. But I'll just show a couple examples. So if G1 is the unique new form of weight 2 with CM, okay, here it is, it has coefficients beta 1. And then G2 is a weight 3 new form again, non-CM. Then one conjecture is that the number of complete subgraphs of order 4 in G3 of P can be written in this way in terms of the Fourier coefficients of those 2 modular forms. And then I'll show one more conjecture, but I'll go through it kind of quickly. So here's 4 more new forms. 2 of them are weight 2, 2 of them are weight 3. Their coefficients are gamma 1 through gamma 4. We also want gamma 5 to be this 3f2. And so here's another conjecture. If P is a prime that's 1 mod 8, then we think that K4 of G4 of P can be written in terms of all of these, the Fourier coefficients of those 4 new forms, and then this 3f2. Okay, so I think the connections are much deeper than what we know so far. with modular forms, especially of higher weight. That's the case I think is cool. Okay, so let me get into some of the proofs of these theorems. And so I'm going to talk first about just counting vertices and edges. So this is a little bit of graph theory, but it's also going to get into a lot of hypergeometric function stuff that we know. And so it turns out to prove our theorems, we're going to need the generalized Paley graph as well as 2 subgraphs of the Paley graph. These are going to be really important. So the first subgraph we're going to take is hk of q. So this is the subgraph of gk of q, where you only keep the vertices that are already kth power residues. So they're already kth powers. Induced just means once we throw away everything that's not a kth power, all the edges that are between the vertices that remain should still be there, right? So you keep all the edges that were in the original graph that are connected to these vertices that are kth powers. And then hk1 of q is the induced subgraph of hk of q, where now you're only keeping neighbors of 1. So you're only keeping the vertices that were connected to 1 in hk of q. So this proposition is going to have 6 parts. We're going to count the vertices and the edges of all 3 of these graphs, and this is going to be essential to our proof. So first, gk of q. Well, the vertex set is fq. So there's q vertices. And the number of edges, so this is like talking about how many differences of elements are kth powers, right? Because you have an edge between 2 vertices if their difference is a kth power. So there's q minus 1 over k kth powers. And so if you fix any vertex, then the number of edges coming out of it is q minus 1 over k. And then you do that for all q vertices, so you multiply by q, but then you've counted each edge twice, right? Because the edge connects to 2 vertices, so then you divide by 2. Okay, so these are a little bit more difficult. For hk of q, you're only keeping vertices that are kth powers. And so there's q minus 1 over k of those. And then for the edges, so this I'm actually going to write out in a proof. For the edges, this is where the Jacobi sums come in. And then once you go down to hk1 of q, the number of vertices has to do with the Jacobi sums, and then the number of edges has to do with the 3f2. Okay, so I'm gonna go ahead and prove those more difficult things right now. So first we need to make a few observations. If you're in the Paley graph, you have an edge between a and b, if and only if a minus b is a kth power. So chi k of a minus b is 1. So chi k is like a character of order k. If you're in hk of q, the vertices each have to be quadratic or kth power residues as well. And so now you need chi k of a and chi k of b to also be 1. And then when you go all the way down to hk1 of q, everything also has to be a neighbor of 1. So you have to be connected to 1 by an edge, meaning you also need these 2 conditions where chi k of 1 minus a and 1 minus b are both 1. Okay, so now I'm going to show a few more formulas of green. So green proved 2 really nice formulas. One for 2f1, where he was able to show that you can write q times 2f1 of a, b, c, lambda as a sum over elements of the finite field of this. So you have, some of the characters and then applied to b, and then some other ones are applied to 1 minus b, and some other ones are applied to b minus lambda. So this kind of looks like what we had in the previous slide, right? So if you choose the lambda correctly, this will be really useful. He also proved a formula for 3f2, and it looks like you plug in a, and 1 minus a, and b minus 1, and a minus lambda b. So that looks even more similar to like this last thing that we had at the bottom here, right? All those conditions. And so this is going to help us relate the hypergeometric functions back to these graphs. We're also going to need character orthogonality. So this is a pretty basic result. If k is at least 2 and q is a prime power that's 1 mod k, then basically what this is saying is if you add up all the powers of chi k of b, right, the powers going from 0 to k minus 1, you get k if b is a kth power, and you get 0 if b is not a kth power. So you can use this to calculate the degree of any fixed vertex A in hk of q. So the degree is the number of edges coming out of it. And so if you use this character orthogonality, then you can write that as like the number of other vertices that are quadratic residues, meaning you need this chi k of b here, that are also connected to A. So you need A minus B here as well. Okay, and we need the 1 over k squared because we've used the orthogonality here to write these. And that you can write in terms of Jacobi sum. So this here, the sum of these two characters applied to B and A minus B, that looks just like a Jacobi sum. Okay, so then if you go down and look at HK1 of Q, so now everything has to be a neighbor of 1 as well. And you look at the degree of the vertices there, we're going to use character orthogonality again, and we're going to get this guy here, which looks just like the 2F1, right? The formula of green for the 2F1s. And then the number of edges, how to find the number of edges is you look at the degree of each vertex, you add all of those up, but then you have to divide by 2 because you counted everything twice. And so we get 1/2 the sum of all the degrees as the number of edges. But when you take a trace of 2F1s, you get a 3F2. And that's by green. And so then that's how you get the formula in terms of the 3F2 for the number of edges in HK1 of Q. Okay. So I think it's kind of neat how these character sums show up in graph theory, because I would not have expected that, but it's pretty cool. Great, so that's the proposition. Now, why does that help is the big question. So we looked at these subgraphs. How does that tell us anything about our result? Well, there's a lemma that we proved in graph theory that says if n is a positive integer, then the number of complete subgraphs of order n plus 1 in the Paley graph is related to the number of complete subgraphs of order 1 less than that, order n, in HK of Q. So all you have to do is multiply by Q and divide by n plus 1, and then you can count smaller subgraphs of HK of Q. And then we have a similar formula that says the number of complete subgraphs of order n plus 1 in HK of Q can be written in terms of the number of complete subgraphs of order n in that subgraph HK1 of Q. And so if you kind of like do both of these at the same time, you get this formula for the number of complete subgraphs of order n plus 1 in the Paley graph in terms of the number of complete subgraphs of order n minus 1 in that second induced subgraph. So the cool thing is all we wanted to know was the number of complete subgraphs of order 4. And 2 less than 4 is 2. So then all we have to do is count the edges of that second subgraph. Okay, so this lemma plus the proposition is the entire proof of the theorem. So once you count the edges of that second induced subgraph, then you automatically know the complete subgraphs of order 4 in GK of Q. So I'll include a little proof of this as well. This is more of a graph theory proof than a hypergeometric functions proof. So if you look at the Paley graph and you take a subgraph with the vertex 0 and n other vertices, well, that's complete, meaning every single edge that could be there is there. If and only if, well, first of all, everything has to be connected to 0, meaning that each thing itself is a quadratic residue or a kth power residue. And then all the differences also have to be kth power residues. But that's the same as just saying if you pluck out that vertex at 0 and you leave the rest of it, that's a complete subgraph in HK of Q. Okay. And so if you do that for, I'm not going to talk about the automorphism, so that's the formal way to do it. Basically, if you fix, like we fixed 0, if you fix all the vertices, like 1 by 1, the same thing happens each time. And so you like multiply by Q and then divide by n plus 1 because you've repeated each subgraph n plus 1 times because that's how many vertices were there. So that's why we have this Q over n plus 1. And then you can do a really similar thing for HK of Q down to HK1 of Q. If you take the subgraph with 1 and then n other vertices, that's complete if and only if, well, we're in HK of Q, meaning each thing itself is a quadratic residue. All their differences have to be quadratic residues because it's complete. And then they're connected to 1. So if you subtract 1, you should still get a, I keep saying quadratic residue, you should still get a kth power residue when you subtract 1. So then again, if you pluck out that vertex at 1 and you leave the rest of it, that's a complete subgraph of HK1 of Q. You have to repeat that for each fixed vertex. So there's Q minus 1 over K of those. So that's the Q minus 1 over K. And you've repeated each one n plus 1 times again, because that's how many vertices are in each graph. So you divide by n plus 1. Okay, So that's the proof of the lemma. And then to prove the main theorem, so to prove theorem 1, you use the proposition to count the number of edges in HK1 of Q, and then the lemma automatically tells you the number of complete subgraphs of order 4 in GK of Q. To prove theorem 2, that was just the number of complete subgraphs of order 3. You only have to go one step up. Okay. Great. All right, now the proofs of the corollaries, those were the lower bounds for the Ramsey numbers. That required significantly more work, actually. And it's because we actually had to evaluate these hypergeometric functions, and that's not easy. And so the bulk of the paper, like 10 or 12 pages of the paper, is just trying to simplify these hypergeometric function evaluations so that we could come up with exact formulas that didn't have 3F2 in them, where we actually evaluated them. And then we could tell where they're 0. And so we had to use reduction formulas for hypergeometric functions that look kind of like this. So reducing from like 3F2s to 2F1s. We also had to use these transformation formulas. There's a bunch of these where you have a 3F2 and all these characters inside, and then you kind of change the characters around, and those are equal. Okay, so those were really useful. We ended up with 10 distinct cases depending on, remember the sum that we had that the finite field hypergeometric function was inside? It was over like T1, T2, T3, T4, T5. So it was like a 5-fold sum. And you end up with 10 distinct cases depending on what those T's are. We had to like introduce this other notation because everything was so messy with the Jacobi sums. We ended up defining this set of this T1 through T5. So these are like all the things that we had to actually look at with all these restrictions on them. And so we had to prove this intermediate theorem based on those 10 cases. So there were 10 cases. We calculated for each of them what this main theorem looked like, and then we like added them all together. And this is what we got. So we still have this part at the end that we couldn't quite simplify. We're gonna have to use the information about the hypergeometric functions to do that, but the rest of it simplified pretty nicely if we chose certain T's. And so here's just a quick bullet point list of the rest of the proof. So each transformation formula for the hypergeometric functions induces a map from xk to itself. So xk is that set of the T1, T2, T3, T4, T5. The group generated by that looks like S4 and it acts on xk. And that hypergeometric function evaluation, that's going to be the same for all T in each orbit. And so you only have to do it for each orbit representative. And that's how we calculated it. So it took a good bit of work to actually evaluate these things. But then we tried to find the largest Q for each K equals 2, 3, and 4, for which you get 0 in the formula. And then when we found the largest Q so that you get 0, that's a lower bound for the Ramsey number. Okay. Great. So I just want to summarize. It's a long summary here because we did kind of a lot, and then we had all these connections that we proved and conjectured about the modular forms. So the first thing we did is we looked at these generalized Paley graphs, right? And we tried to count the number of complete subgraphs of order 4 and the number of complete subgraphs of order 3. Those are the triangles. And so we ended up with these crazy formulas that are like, this one's a 5-fold sum, this one's just like a 2-fold sum in terms of 3F2, and then these Jacobi sums here for the triangles. And then as corollaries, we got lower bounds for the Ramsey numbers. Remember the third one for K equals 4, those did not match the best known lower bounds, so we were a little disappointed, but the first two did. So we would need to think of, some other graph to look at other than the generalized Paley graph to try to get a better lower bound for these K equals 4 cases. We also got another corollary based on a known formula for the Fourier coefficients of some weight 2 new form. Maybe it was weight 3. I'd have to look back. And we can relate them directly back to the number of complete subgraphs of order 4 in the Paley graph. So that was really nice. And then we conjectured some other relationships between modular forms. And so all of these involve kind of higher weight modular forms, meaning weight higher than 2. So the interesting cases are where you have a weight 3 new form, or even higher than that. there have been some examples of, weight 6 or 8 or 10 or 12. So those are really, really interesting. So we've conjectured these two more relationships with the Ramsey theory on the left, and then involving these Fourier coefficients of these higher weight new forms on the right. And again, we're in the process of finding more conjectures. So we've identified 13 conjectures. And we are currently writing a paper for a conference that's going to happen at Baylor, hopefully in the spring. It's been postponed since last spring, but we're writing a paper for that conference proceedings. And so hopefully we will have all those conjectures in there, as well as like a nice summary of all the modular forms, or a lot of the modular forms that appear in the study of hypergeometric functions. And a lot of those, just based on what I went through in this talk, can be related back to the number of complete subgraphs of orders 3 and 4 in the Paley graphs. Okay, so that's all I got. Thank you.
All right. Well, thanks, Maddie, for a very nice talk. Yeah, it's cool to see modular forms being connected to this stuff. Any questions for Maddie?
I have some, yeah. I guess the first one is just kind of, is there like a candidate in the graph theory world of something that's like self-complementary, but maybe not undirected, as like a better thing to use for this like K4, or the last case where your inequality didn't match up?
Yeah, that's a good question. I don't know one. I don't know, but it'd be nice if there was. I guess I don't know that it would be nice from a number theory perspective, because the thing that's so nice about the Paley graphs is that they're defined by this kth power stuff, like using the characters. And so if you find some other graph that is self-complementary, or that is a natural choice, you might not be able to use as much number theory on it to prove things. So that might be more of like a purely graph theoretic thing that I would probably not be able to figure out. But yeah, I hope that there's a better one, because then, maybe people will be able to find better bounds for the Ramsey numbers, or like calculate them exactly. Yeah.
And then I have one other question. So you had this lemma where you can go from something order like n to n minus 1 and then n minus 2. Mm-hmm. Is there like some intuition as to like, because you have some subgraphs induced by something, is there some intuition on like how to choose those? Or is there like a reason why you couldn't just always pick some clever subgraph and get from like n to n minus k for whatever k you want, or something like that?
So the reason, let me go back up to the lemma. The reason that we chose, so remember we fixed a vertex and then looked at like some arbitrary other n vertices. The reason that we fixed like the vertex 0 when we were going from gk of q to hk of q is because if the vertex 0 is in that complete subgraph, and that means each of these n vertices is connected to 0, meaning their difference is a kth power. And so that looks like chi k of ai is 1, meaning then you're in hk of q, right? These vertices are in hk of q. So that's why we chose 0 there, because then you would end up with a subgraph that is in hk of q.
Yeah, I guess my question is like, can you define some subgraph like HK1, or because you have HK, then HK1, where you pick out like that one, can you continue doing this and like pick out like, hey, define a subgraph HK2?
Like go farther?
Yeah, and continue going, because right, you could stop at like the 4 Ramsey number because you got down to like order 2 where it's easier to count things. Like, is there any reason you couldn't get bounds for like the R5, R6, and so on if you have some clever way to just like descend like this indefinitely?
Yeah, I feel like I had that thought at one point as well, and then didn't go anywhere with it. I'm not sure if it would be as easy to keep going here, because like 1, that you can take neighbors of 1 to be a subgraph of hk of q, because 1 is a kth power.
Right.
And so then past that, you'd have to be able to find something else that is a kth power and a neighbor of 1, And I don't know that that would be like the same thing that you would choose for any, you know what I mean?
Right. Okay.
Like 0 was a natural choice and 1 was a natural choice for this other subgraph. I don't know off the top of my head what the next natural choice would be, but that's a good idea. Like it seems like you could just extend this further and like keep doing subgraphs. It also seems like you'd be able to use this formula to like we also know, this is like a vague idea that I've had that I haven't tried. You can go from K2 of HK1 of Q up to K4 of GK of Q, right? So that's what we did. We went from edges of HK1 of Q up to complete subgraphs of order 4. So I guess I don't know why we wouldn't be able to like start at, so I guess the reason is because we don't know this, but if you could like start at 3, like complete subgraphs of order 3 and HK1 of Q, if you could somehow figure that out, then like could you, but that's probably related to what you said, because if you can do another subgraph and then relate that to the edges of this other subgraph, then yeah, maybe you could like continue this process. So I don't know. I don't know if there's anything there. I think it would be cool if there was, because then we could go higher than subgraphs of order 4. And that's like hard. Like it's hard to look at subgraphs of order 5. Those are like way bigger, right? Because it has all the edges. Like it's not just a pentagon. It's like the pentagon and everything in between. So that would be a cool thing if we could say something about that.
It might be, actually, I don't know. Like it might be for like k equals 2, these are just quadratic residues, right? So maybe there's like a natural choice at least there, but
Oh, maybe.
I don't know about for these kth power residues, like how
Yeah.
easy.
Yeah, I'm not sure. That's a good question.
Yeah, so Maddie, Michael Griffin and I wrote something a long time ago about some of these character sums. So the
Okay.
formula for that Green gave in his PhD thesis for the hypergeometric finite field sums in terms of traces of lower ones, right? I guess this is the analog of the Euler integral transform in the classical hypergeometric case.
Okay.
But anyway, yeah, so that's controlled by these Jacobi sums, and well, you know, so you get a linear combination of the lower order things. So Michael and I looked at something that Ken suggested to us. He noticed that if you do the linear algebra kind of thing, and you say this is like some kind of linear transform. So this is determined by some matrix of values that are determining these linear combinations. All right, and if you look at that matrix of values, things actually turn out to be quite nice. And at least in some cases, you can completely, and that's what Michael and I wrote down, is you can actually write down the characteristic polynomial of those matrices, determining those transforms explicitly.
Okay.
So in cases where you knew something about the Jacobi sums, so in particular, at least one of the examples you gave was exactly the one that we looked at, where the top row is all like the same character, like chi sub k or something, and the bottom row was epsilons. And you had one where it was basically that, but one of them was a conjugate of the others. So I would think that would be similar enough. But I just wonder if it could be useful that, so basically Ken wanted Michael and I to look more into the applications to elliptic curves and things of these formulas that we were discovering that he conjectured on the computer. And we never really got around to that, but Ken thought there should be more interpretation. And there's some similarity to the types of formulas you use, and just from the linear algebra point of view, maybe there's something like useful about like knowing those characteristic polynomials and, traces and determinants and whatever you want to know is all very explicit. So there's, and in fact, we even, for the eigenvalues, I think we even wrote down some of the eigenvectors completely explicitly.
Wow.
So that kind of thing maybe could be useful.
Yeah, that would be great.
I'm not sure exactly how it's connected, but it's been a long time since I thought about this stuff. That was like 8 years ago, but rang a lot of bells, and Ken always wanted us to do more of that. I mean, Michael and I just like never got around to it, and he felt that there should be more meaning behind the stuff we were writing down. But it's a very short thing. It's only like a 5-page paper or something. So.
Okay. Yeah, that's great. I'll definitely look for that. Thank you.
Yeah, if you look up our names, or it's pretty easy to find. It's
okay.
I have a few papers with Michael, but it's certainly the only one with the word like hypergeometric in the title or something like that.
Okay. All right. Yeah, I'll look for that.
But yeah, if there's anything related, I'd be happy to discuss it with you.
Okay, great.
I could return to that old project.
Yeah.
Yeah. Any other questions for Maddie?
I have one more if no one else does. So in these conjectures, I think you put it quickly on one of the slides.
Yeah, there's not a ton of information here. I can go back to the other ones if you want to see.
It had to do with the new forms.
Okay.
So you have this connection to like elliptic curves, right?
Yeah.
And you're choosing like a prime power, so it feels like there's something. This isn't like a well-formed question, but do all these elliptic curves have like complex multiplication by something related to like the prime that you're choosing for the graph? Is there some connection between like your new form having complex multiplication and like something to do with these residue symbols?
Yeah, that's a good question. And I don't know the answer to that, but that's actually something Dermot was really interested in. And I don't know that we haven't gotten around to like looking into it yet, but he thought it was interesting that some of these that come up are CM and some are not. And so he wanted to like sit down and write down all the examples of ones that are and ones that aren't and try to figure out if there's a relationship to like what type of thing you're looking at and the graph theory. So I don't know, but
that answers part of my question. I was wondering if there was any that weren't CM.
Let me go back to so this one, like H1 has CM, H2 and H3 have CM, but H4 doesn't.
H4 doesn't. Is it like a twist of something though that maybe, I don't know.
Oh, I don't know. I'm really bad at just eyeballing these things.
Yeah, I wouldn't be.
Ken would probably just be able to like say, like look at it and say, but I don't know.
That would be super interesting though, if you could.
Yeah, so this other conjecture, we had one CM form and then the other one's non-CM.
Okay.
So I don't know, but that is another good question that we want to know, like why, like how that works.
But even more, so like the fact, like you have this conjecture where it has CM by Q joined square root of -3. Is it like, I guess you can choose any prime that's 1 mod 6. So maybe you can't see it. I was just wondering if you could somehow see it from the graph side, like predict what field it would have CM by.
It's possible. I would suspect you would. I mean, I feel like it would be hard to see a direct connection to the graphs. I think it might be easier to see a direct connection to the hypergeometric function evaluations, because that's really like the middle point. And so it might help if you look at the middle point first and then relate that back. But yeah, I don't know. That's a really good question. Yeah, I think all these connections are really awesome. And I think that they're more interesting to me because I don't fully understand them yet. So I want to know more about like how everything is related here. And I don't have a great answer yet. So,
Ian, are you getting at just like you have the number of K4, there's some kind of bijection between something involving complete 4 complete graphs, subgraphs, and number of points over finite fields of elliptic curves in some cases, or there's some weird.
Yeah,
like is there like a direct way of or either that or like eigenvalues of Hecke operators? There's some weird correspondence, but you're asking, your idea is basically like your question is philosophically like, is there a direct way of seeing all these connections?
Yeah, I guess, or like, is there a reason, like, since these are still conjectures, is there like, maybe some philosophical reason we should believe that like some count of like a CM elliptic curve should show up for these graphs or something like that, other than like we know they're both connected to hypergeometric functions?
If there is an interpretation, I don't know if it's more likely for that, like point counts of CM elliptic curves over finite fields, or the fact that these are like eigenvalues of Hecke operators, and there are things involving Hecke operators and graphs and stuff, but it could just be a dimensionality connection,
So I don't know if this helps, and this is probably exactly what you were talking about, Larry, but in our paper that we're writing up that has all these examples that have been found of connections. So our paper is really about hypergeometric functions and not about the graph theory. but a lot of these formulas that have been found come from traces of Hecke operators. And depending on like the dimension of your space, those might just give a formula for the Fourier coefficients of like the one generator of the space, or if you have more, then it'll be like a linear combination of those.
Right.
So I don't know if that.
Yeah, and these connections, the Calabi-Yau threefolds and stuff, I mean, they're very sporadic and special examples. There's not like a, to my knowledge, there's not a general theory of how modular forms are connected to those things. There's just a bunch of special examples people know, but I don't think it's in a comprehensive framework at all.
Yeah, I think you're right.
But yeah, there's lots of these fascinating connections that it's very tempting to say, is this, you know, part of some infinite family or some very general picture? And I think a lot of people have thought about that and not
like,
found
maybe
a completely general picture. But
yeah, I guess it doesn't have to be true. It just seems like there's a lot of examples. So yeah.
Yeah. All right. Well, it looks like a couple people had to leave. It's something else. But yeah, if there's no further questions, let's thank Maddie again. Yeah.